Hello class, welcome to this video on AP Statistics, Chapter 4, Practice. So we're looking at the multiple choice and free response. These are supplemental problems from the book that I gave you in class. Not from the textbook, but from a different book here. Alright, so number one, data were collected on 20 cities and the percentage of women in the workforce. Data were collected in 1990 and again in 1994. Gains or losses in this percentage were the measurement upon which the study's conclusions were to be based. What kind of design was this? So we have 20 cities, so let's just picture some of them. Let's say these cities, these dots represent the cities. We'll just do like 5 cities. So let's say 5 cities in 1990 and 5 in 1994. Right, so what we're looking at is the gains or the losses in the percentage of the women in the workforce. So we're taking a look at the difference between two cities. And so this is a matched pair, guys. So we're taking the same city and we're taking the same city over 2 different time periods, right? So it's a matched pair, right? So it's like sort of like when you have a treatment and then you do it on the same subject, right? So it's kind of like the same thing, but there's no treatments imposed here. It's just observing, what's happening, measuring the data. You're just looking at the data in 1990 and then looking at the data in 1994. So this is not an experiment. This is just an observational study. So it's got to be an observational study. It's not an experiment, right? Because we're not imposing any treatments here. Now we got matched pairs, like we said, because we're looking at the same city in these 2 different periods. Therefore, it's a matched pairs design. So matched pairs design does not mean that it's an experiment. It just means that you have matched pairs like this. Now, in this case, this is a matched pairs design built into an observational study. So the answer is E here. All right, so let's look at the next one, number 2. You want to do a survey of members of the senior class at your school and want to select a simple random sample. You intend to include 40 students in your sample. Which of the following approaches will generate a simple random sample? So again, simple random sample, that means that you're taking a population, you're numbering them, right? Or if you label them, let's say number 1 through whatever, and then you're randomly selecting some numbers, right? So then you do it randomly, right? So let's say you select that one, select that one, select that one. So that's a simple random sample. So everybody has every sample that you select has an equal chance of being selected. So a sample of 268 has the same chance of being selected as a sample of 1, 2, 3, 4 and 1, 2, 3, right? It's funny because you normally won't think that as think of this as this having the same chances because it's 1, 2, 3, or you normally wouldn't think of that as random. But remember, random is just due to chance. So this has got to be the same outcome as this, right? As any other outcome. So you intend to include 40 students in your sample. Which of the following approaches will generate a simple random sample? Write the name of each student in the senior class on a slip of paper and put the papers in a container. Then randomly select 40 slips of paper from the container. So that looks pretty good. You're putting the names of each student on a slip of paper and then putting them, and then of course we're assuming that we mix them up, and then you select 40 slips of paper from the container. So this looks pretty good. Let's look at the other ones. Assuming that students are randomly assigned to classes, select 2 classes at random and then include those students in your sample. Okay, so now notice that A and B so far are probability samples. So what's a probability sample? So a probability sample is a sample that is obtained where the members that you select in in your sample all have a chance of being selected. Now they could have different chances of being selected. They don't have to have the same chance of being selected. So in a simple random sample, right, each member, each sample of a certain size, so let's say you're looking for 40 students, right? Each sample of 40 students has the same chance of being selected, right? So in order to do that, you'd have to number all the students or whatever, and then randomly select them, right? From that pool. Or randomly select X amount of students and then pick 40 of them. But each group of 40 students is equally likely to be selected, right? That's what we're looking at here. Now, when if we look at part B, that's a probability sample, but it's not a simple random sample because each group of, say, 40 students is not likely to be selected. So, for example, if let's say I had a classroom where you have A, student B. Let's just make it 2 students just to make it easy. Then you got student C, student D, and then let's just look at one more classroom, E and F, right? So let's say you had those 3 classrooms. Now, if I randomly choose 2 classrooms, right? So let's say I choose this one and this one, classroom 1, classroom 2, classroom 3. Well then, okay, so then now I got a sample of A, B, E, F, right? And notice that there's not all groups are equally likely here, right? Because we would exclude certain groups of sample 4, because the only possibilities here are A, B, E, F. Then you got A, B, C, D, right? Then you have C, D, E, F, right? So you got 1, 2, 1, 2, 1, 2. So you only got 3 possibilities here. You see what I mean? And so you have a probability of 0 for the following situation. If I had A, C, E, right? A, C, E, or let's just say A, B. Let's just mix and match here. A, B, C, E. There is 0 possibility of getting A, B, C, E. And so notice that this is a probability sample because the probability of getting these ones is 1/3, right? However, the probability of getting this one is 0. And that's what I mean. So this is not a simple random sample, okay? So it cannot be B. From a list of all seniors, select one of the first 10 names at random. Then select every nth name on the list until you have 40 people selected. Okay, so now for part C, this is known as a systematic sample. If from a list of seniors, select one of the first 10 names at random, select every nth name. That's systematic sampling, right? Systematic. So that's not simple random sampling as we know it. So systematic. And then select the first 40 seniors to pass through the cafeteria door at lunch. That's not even a probability sample. So systematic is a probability sample. So for the first name, there's a 1 in 10 chance that the first 10 names are selected, and then there's 0 chance that the other names are selected, right? For the first 10 names, right? So that changes the probability, right? That is a probability sample, but it's not a simple random sample. And B and A are they're probability samples. And A is a simple random sample, probability sample. Now D is not even a probability sample because you're just selecting the first 40. That's convenience sampling, right? And then E randomly selects 10 students from each of the 4 senior calculus classes. All right, so randomly select 10 students. That kind of sounds similar to part B, right? Where you select 2 classes random, include those students. But for part B, this is a cluster sample. So let me write this. This is cluster sampling. You select 2 classes and then include those students. Now in this right here, E is a stratified sample. So you're looking at 4 classes, right? 4 senior classes. And then you're randomly selecting 10 students from each, right? So this is stratified, so it's not simple random sampling. Now, the reason why that each thing doesn't have the same chance is, like, for example, if I look at the same example here, I can select, for example, A, C, and E, right, randomly from each class, right? And then, but I cannot have A, C, E, or I cannot have A, E, F, right? So A, E, F would not have the same chances of being selected as A, C, E. And so, hence why it doesn't have doesn't follow the definition of simple random sampling. All right, so hopefully that idea of same probability for samples kind of makes sense. All right, so for number 3, which of the following is or are important in designing an experiment? First, control of all variables that might have an influence on the response variable. So that would be like controlling confounding variables. So that makes sense, right? We need to have that. Randomization of subjects to treatment groups. So yep, random assignment, right? So randomization is important in designing an experiment. Use of a large number of subjects to control for small sample variability. Yeah, so if you use more subjects, you reduce the variability of the sample, and so that's what we're looking for. That's called replication. So this is true. So the answer is D, all 3. All right, number 4. Your company has developed a new treatment for acne. You think men and women might react differently to the medication, so you separate them into 2 groups. Then the men are randomly assigned to 2 groups, and the women are randomly assigned to 2 groups. Okay, so you have the men and women might react differently. So we have to keep that in mind, that men and women might react differently. So you separate them into 2 groups. So men are randomly assigned to 2 groups, and women are randomly assigned to 2 groups. One of the 2 groups is given the medication, and the other is given a placebo. This basic design is, so that's blocking. So you're blocking by gender because you're saying the men are going to react differently, women are going to react differently. So you're blocking by that. It's not completely randomized. Blocked if you have a block design, that means it's not completely randomized, right? So, because for completely randomized, you're not breaking them into groups, right? Like blocks. So this is just a block design. And it's not match pairs, because remember, match pairs is when you're looking at the same subject in different conditions. You're looking at comparable subjects with 2 treatment conditions, which is not what you're doing here. So you're blocking by gender. All right, so answer's got to be B. Let's look at the next one. A double-blind design is important in an experiment because A, there's a natural tendency for subjects in an experiment to want to please the researcher. So yeah, that's possible. There's definitely possible. So I'll put it there. It helps control for the placebo effect. So placebo effect, that's important. So this is why we blind, so that if they don't know what they're getting, so that helps control the placebo effect. Evaluators of the responses in a study can influence the outcomes if they know which subjects are the treatment group and which are in the control group. The researchers are being blinded, and so if they weren't blinded, they could potentially interpret the data differently. Part D, subjects in a study might react differently if they knew they were receiving an active treatment. Yes, they might react differently. So all these are correct, so it's got to be E. Okay, so let's look at number 6. Which of the following is not an example of a probability sample? So again, we mentioned what a probability sample was. We gave you a few examples of that. A simple random sampling, anything that has an element of some kind of randomness, where there's chance involved, is a probability sample. Something that does not involve chance is not a probability sample. Okay. So that's just kind of to give you an idea. All right, so you're going to sample 10% of a group of students. You randomly select one of the first 10 students on an alphabetical list, and then select every 10th student after that on the list. Okay, so that looks like a lot like a systematic sample, which is a probability sample. So it cannot be this one, because that looks like systematic. You are a sports talk radio host interested in opinions about whether or not Pete Rose should be elected to the Baseball Hall of Fame, even though he has admitted to be betting on his own teams. you ask listeners to call in and vote. So here you're asking for a poll, right? And you're asking listeners to call in. This is not a probability sample, all right? So it's got to be this one. This one looks good, but let's look at the other ones. This does not have a chance. It's not like you're doing this by chance. You're just asking people to volunteer. A random sample of drivers is selected to receive a questionnaire about the manners of Department of Motor Vehicle employees. Again, you got a random sample is selected, so this might be like a simple random sample or something like that, so it can't be that one. In order to determine attitudes about the Medicare drug plan, a random sample is drawn so each age group is represented, so that's a probability sample. And choosing respondents for a survey in a large city, interviewers choose homes to survey based on rolling a die, so that's based on chance. All right, so it's got to be B. All right, so number 7. So which of the following is true of an experiment, but not of an observational study? A cause and effect relationship can be more easily inferred. Yes, in an experiment, because if you have random assignment, then which is a element of a well-designed experiment, then you're going to have you're going to be able to do a cause and effect relationship, assuming that you have statistically significant results, right? So that's why they said can be more easily inferred. And then the cost of conducting it is excessive. It says it has to be true of an experiment, but not an observational study. Observational studies can also be costly. So this is not necessarily true, because observational study, you're still going out in the field, you're still grabbing your you're still polling people and things like that, and so it takes a lot of resources, regardless of whether you're doing an experiment or observational study. All right, more advanced statistics are needed for analysis after the data are gathered. Not necessarily, right? You're just comparing results just like you would for an observational study. The only difference is that you're controlling for variables, right? So that's not necessarily true. By law, the subjects need to be informed that they are part of a study. So this is called informed consent, right? Informed consent is not just an experimental thing. It's there's studies that do that, observational studies or experiments. So it's not necessarily something that's exclusive to an experiment. Possible confounding variables are more difficult to control. That's not true for an experiment, right? Because we see that confounding variables are generally something that we do in an experiment. So that's not the best answer. The best answer is A. All right, 8. A study showed that persons who ate 2 carrots a day had significantly better eyesight than those who ate less than 1 carrot a week. Which of the following statements is or are correct? This study provides evidence that eating carrots contributes to better eyesight. Provides evidence that eating carrots contributes to better eyesight. Now, when they say the word contributes, they mean causes, right? So eating carrots causes better eyesight. Now, this is an observational study, right? You're just looking to see if they ate 2 carrots and then if they did not, or if they ate less than 1. So this is an observational study, so it can't be 1. We could say there might be a correlation, but definitely not a contributing factor or causation. The general health consciousness of people who eat carrots could be a confounding variable. So this is what I'm saying. This is an observational study, and people that eat more carrots could be generally more health conscious, right? And that could be a confounding variable. And so if they're more health conscious, they might actually go to take more visits to the eye doctor, or they might have better diet in other areas rather than just eating carrots, right? So it might be that their diet includes more carrots, but it includes other healthy foods as well besides carrots. And people that don't eat carrots don't eat as many veggies in general, and that would contribute potentially. All right, so this looks pretty good. So I'm going to cross this one out, and then this one looks good. All right, so now we got, this is an observational study and not an experiment. Yes, this is an observational study. So the answer is D. Sorry. D. So which of the following situations is a cluster sample? All right, so let's look at that. Surveys, cluster sample. Survey 5 friends concerning their opinions of the local hockey team. Survey 5 friends. So this is a convenience sample, so this is incorrect. So A is a convenience sample. You're just surveying your 5 friends. Take a random sample of 5 voting precincts in a large metropolitan area and do an exit poll at each voting site. So you're doing a random site. So you have 5 voting precincts. So you're choosing 5 precincts, right? And then you're doing a sample of each precinct. So that sounds a lot like a cluster sample. So that looks pretty good so far. Measure the length of time each 5th person entering a restaurant has to wait to be seated. Each 5th person entering a restaurant has to wait to be seated. That looks a lot like systematic. So it's not that one, that's systematic. From a list of all students in your school, randomly select 20 to answer a survey about internet use. That looks like simple random sampling. So it's not that. And then identify 4 ethnic groups at your school. From each group, choose enough respondents so that the final sample contains roughly the same proportion of each group as the school population. So those are the ethnic groups. And then from each group, that was stratified. So it can't be that one. So it's got to be B. All right. Okay, so that's it for the multiple choice. So we're going to start the free response. All right, so let's look at number 1. You are interested in the extent to which ingesting vitamin C inhibits getting a cold. You identify 300 volunteers, 150 of whom have been taking more than 1,000 milligrams of vitamin C a day for the past month, and 150 of whom have not taken vitamin C at all during the past month. You record the number of colds during the following month for each group and find that the vitamin C group had significantly fewer colds. Is this an experiment or observational study, and explain? What do you mean in this case when we say that the finding was significant? All right, so first off is an observational study. The researcher, there's no treatments imposed, right? So observational study, no treatment imposed. And here they're volunteers, so participants self-selected themselves for this into either group, right? So it's not like you're randomly assigning them into groups or anything like that. And now they said, what does it mean to say that your finding was significant? Well, that means that the difference in the groups in the vitamin C and the non-vitamin C group was way too big to attribute to chance alone. Okay, so that's what it means when you're saying something is statistically significant. So that's number 1. I'm going to say some of these. I'm not going to actually write out the answers to some of these. I'm just going to actually say some of them verbally, just because, writing them out is going to take a while. But there's number 1. Number 2, design an experiment that employs a completely randomized design to study the question of whether or not taking large doses of vitamin C is effective in reducing the number of colds. Okay, so again, a lot of these I'm gonna try to not write everything down just because it's gonna take some time, but we can kind of walk you through the experiment. So if you're listening, so you want it to be completely randomized. So you take the 300 volunteers, and then randomly assign them into 2 groups. So randomly split the groups into 2 groups. 150 each, right? 150 for the vitamin C, 150 for a placebo. Okay, so one that looks like vitamin C, but it doesn't have the active ingredient, right? And then you're going to try to make it so that the study is double blind. So you're going to say the subjects and the researchers can't know what treatment is being received or handed. So you want to make sure that no one knows who's getting what treatment, neither the researcher nor the participant. So that's double blind. And then after a period of time, you know, maybe a month or so, whatever the time period frame is, give it some time. And then you're going to count the number of colds in each group. And then you're looking for the difference in the number of colds between the two groups. Okay, so there's a completely randomized design. All right, so for number 2. Number 3, a survey of physicians found that some doctors gave a placebo rather than an actual medication to patients who experienced pain symptoms for which no physical reason could be found. If the pain symptoms were reduced, the doctors concluded that there was no real physical basis for the complaints. Do the doctors understand the placebo effect? Okay, so, and then it says explain. So, so the doctors probably, they don't understand the placebo effect because the placebo effect is a real effect that happens even when you have something that has an inactive ingredient, doesn't have the treatment, you know, the medication or whatever in this case. People often will show a change even with the inactive treatment. There's psychosomatic, psychological, whatever the case may be. If they believe they're receiving the treatment, they might act differently, and then this might all end up showing a change, right? Either the body shows a change or their behavior changes, and therefore the symptoms change. So there's a real basis for this. Now, but we also have to keep in mind that we have no data on what it looks like when we treated them, right? So if you need to compare, like a control group with this group. So you want to see, okay, well, you have the treatment group, and then you have the placebo group, right? And then you might have a control group that doesn't have anything at all. They don't receive any treatment. And then you can see, okay, well, we can compare the placebo to the no treatment and see that, okay, if there's a difference between placebo and no treatment, then that means that there's a real basis for this, right? There's a real physical there's a real effect that is found. But without that comparison, it's hard to actually tell. But the placebo effect is a real effect, and sometimes you need to see if it's significant in certain cases. And so that's how you would test whether it's significant. All right, so number 4, explain how you would use a table of random digits to help obtain a systematic sample of 10% of the names on an alphabetical list of voters in a community. Is this a random sample, or is it a simple random sample? All right, so let's explain how you would use a table of random digits to help obtain a systematic sample. So first off, you're going to get your list. Let's say you got your list of numbers, right? Or the names of each person, right? So you have all these names, and then you can number them, right? 1, 2, 3, 4, whatever. Let's say this is 1 through 10 on the first row. So you need to randomly pick one of those first names. You want 10% of the names, so that means if there's, then what you're gonna do is you need every 10th name for your sample, right? So it just makes it easier. So we'll just say the first 10 numbers, the first 10 names, right, from 1 through 9 can be chosen. So on your table of random digits, right, on the actual random table, you're going to have a bunch of random numbers. So you're going to need to say, okay, pick your first 10 names on the list from 01 to 10, from 01 to 10. Or what you could do, or you can say, 0 through 9. That would also be a possibility. Instead of having 2-digit numbers, you could just do 1-digit numbers, right, from 0 to 9. That would actually make it a little bit easier. So either way, it would be fine, right, whether you do 1 through 10 or 0 to 9. You go to a random table, go pick a random row. So let's say we randomly pick this row. You can use a random number generator to get that if you want, to pick a random row, or just pick a row. And then once you do that, then you look for your first number that pops up, whether it's 0, 1, 2, 3, or 9, whatever, and that will be your first name. So let's say the first number is 3. Then you're going to pick the third person on the list, the third name, or if you're going from 1 to 10, or if you're going from 0 to 9, you know, whatever corresponds to the number 3 on your list. And then you're going to go every 10th member, right? And you keep doing that until you get your sample. Now, is this a random sample? And the answer is yes, it's a random sample. Before you pick the first person, every single individual has the same chance of being selected, right? Now, it's not a simple random sample, right? Because not every sample of, for example, you know, 10 people or whatever is going to be the same, right? Or is equally likely to occur. So, for example, if you have 3 as your first number, there's no way you're going to get 4 in your sample, because you're going to skip from 3 to 13, right? So 3 and 4 ... is not possible, okay? And so that has a probability of 0, which means not every sample is equally likely. All right, so their answer for number 4. All right, so number 5, the Literary Digest magazine, in 1936 predicted that Alf Landon would defeat Franklin Roosevelt in the presidential election that year. The prediction was based on questionnaires mailed to 10 million of its voter subscribers and to names drawn from other public lists. Those receiving the questionnaires were encouraged to mail back their ballot preference. The prediction was off by 19 percentage points. The magazine received back some 2.3 million ballots from the 10 million sent out. What are some of the things that might have caused the magazine to be so wrong? The same techniques had produced accurate predictions for several previous elections. Hence, think about what was going on in the world in 1936. So, in this case, if you look at the data, 2.3 million and 10 million out of 10 million. Well, I mean, considering that they're mailing to their subscribers, there's a voluntary response bias here, right? So, in the around 1936 or so, this was during the Great Depression. So that may have also affected their views on who they wanted to be their leader, right? And so those who mailed or who volunteered to mail in their ballots were most likely to have a strong opinion, right, about who they want to be their leader. So that's something to keep in mind, is this whole voluntary response bias. Also, there's a reason why the other ballots were not sent out. So we also have a non-response here, right? And for some reason, those ballots were not sent out, right? So maybe they didn't have as strong an opinion, but they would have changed the vote had they voted, right? So there's different factors affecting this, but you basically want to make mention of the biases here in the election, or in this election, right? In this study. Okay. All right. For number 6, interviewers after the 9/11 attacks asked a group of Arab Americans if they trust the administration to make efforts to counter anti-Arab activities. If the interviewer was of Arab descent, 42% responded yes, and if the interviewer was of non-Arab descent, 55% responded yes. What seems to be going on here? Well, I mean, so they're being confronted by somebody, an interviewer, right? And so there's a response bias here, right? Obviously, the person is there, and they want to, they feel like they want to please or give a response that is maybe more acceptable, and so they may not be truthful, right? So there's a response bias going on here for number 6, right? Number 7, there are 3 classes of statistics at your school, each with 30 students. You want to select a simple random sample of 15 students from the 90 students as part of an opinion gathering project for your social studies class. Describe a procedure for doing this. Okay, so there are several ways to do this, right? You can use a random number generator, right? So number the students from 1 to 90. And then, with unique numbers from 1 to 90, and then use a random number generator to generate 15 different numbers, so no repeats, from 1 to 90, or between 1 and 90. And then and then survey or select those 15 students that correspond to the numbers generated, right? As part of your sample. So that's one way to do it. You can also do write the names of the 90 students on slips of paper and put the paper into a box, the slips of paper, mix it up thoroughly, then draw out 15 slips of paper at random. And then the names on the paper, the names of the students that are selected are going to be in your sample. You can also do a random number table, and so you can do it from 01 to 90, 01 to 90. You want to make sure you include the O. So from 01 to 90, pick a random starting point on the random number table from left to right. Look at 2-digit numbers, right? And then select 15 different numbers, so no repeats, and ignoring numbers, the number 00, and then 91 and up, right? So 91 to 99. So ignoring those numbers, and then you can do that until you get your sample of 15 students. All right, so there's different ways to do it. I just explained 3 different ones for you. All right, so let's take a look at number 8. Question 1 stated in part, you are interested in the extent to which ingesting vitamin C inhibits getting a cold. You identified 300 volunteers, 150 of whom have been taking more than 1,000 milligrams of vitamin C for the past month, and 150 who have not taken vitamin C at all. You record the number of colds during the following month for each group and find that the vitamin C group had significantly fewer colds. So explain the concept of confounding in the context of this problem and give an example of how it might have affected the finding that the vitamin C group had fewer colds. So the concept of confounding is it's possible that there's a variable whose effects cannot be separated from the effects of the vitamin C. In other words, it's another variable besides the vitamin C that could influence the response, meaning it could also cause fewer colds, right? In this case, for example, where we have the groups were not selected randomly, they were volunteers, so it's possible that the fewer number of colds, could be a result of that. There's some kind of reason why that's the case with those volunteers. Now, what you could do is, as an example, you could provide that those that take vitamin C, right, are probably those volunteers that also are health conscious, and therefore, so maybe they take all their supplements every day, including vitamin C, or maybe because they're taking more than 1,000 milligrams of vitamin C, that means they're eating more fruits and vegetables, right? So there could be another reason for why they're not getting the colds, other than just the vitamin C. It might be that they're eating healthy. So that would be a confounding variable, an example of that. Okay. In that case, in order to control for that, you would have to, you'd have to control that variable in order to see whether it was just a vitamin C or not. Okay, so number 9, a shopping mall wants to know about the attitudes of all shoppers who visit the mall. On a Wednesday morning, the mall places 10 interviewers at a variety of places in the mall and asks questions of shoppers they pass by. Comment on any bias that might be inherent in this approach. Well, first off, there's undercoverage bias because it said in there that if it says on a Wednesday morning. So because it's on a Wednesday morning, if people are working, they're not going to be at the mall, right? They're going to be working. So it's excluding those people that are working. So that would play a role in the undercoverage bias. So that's the main bias inherent there. We don't have any other information on other aspects of the study, so we can't really make any other statements on that. So we'll just leave it at undercoverage bias. Number 10, question 2 asked you to assign a completely randomized experiment for the situation presented in question 1. That is, to design an experiment that uses treatment and control groups to see if the groups differed in terms of the number of colds suffered by users of 1,000 milligrams a day of vitamin C and those that didn't. Question 8 asked you about possible confounding variables in the study. given that you believe that both general health habits and the use of vitamin C might explain a reduced number of colds. Design an experiment to determine the effectiveness of vitamin C. Take into account general health habits. You may assume your volunteers vary in their history of vitamin C use. Okay, so now that we know that the confounding variable is the health habits, right? Whether they're health conscious or not, or varying levels of health consciousness. What we could do is we can block for that variable. So we're gonna do that as a blocking variable, right? So the blocking variable is going to be the health consciousness. Now, what you could do is do a survey of the 300 volunteers to determine their levels of consciousness, health consciousness, to see, okay, what do they eat? Okay, these guys are not health conscious. These guys are, based on the results of your survey, right? So you can do that. Once you figure that out, then you can block by health conscious and not health conscious, right? That would, and then once for each block, then you're going to randomly assign them into 2 groups, right? So let me, I'll do a diagram for this one so you can give you an idea. So I'll actually draw on this one. So you got your volunteers, you have your 300 volunteers. These are your experimental units, okay? And then you're going to break them up. You're going to do blocking here. Okay, so we're going to break this up into 2 blocks, or let's just say 2 or 3 blocks. Let's just say 2 blocks, whether they're health conscious or not. So let's say, or maybe you have different levels of health consciousness. However way you want to do it, break them up into at least 2 blocks. The first block, block 1, is they're health conscious. Block 2, not health conscious. And we don't know how many are in each group because it just depends on the volunteers, right? On the volunteers that you got. And then after we do the blocks, we're going to do random assignments. So we'll do random assignment here. And then we're going to break them up into 2 groups, right? Randomly assign them. Group 1 is going to be use vitamin C. And then group 2, not use vitamin C. And same for this guy. All right, and then once you do that, you compare the results. And you compare the results between the groups. So it might look something like that. Okay, just to give you an idea of the random block design, or yeah, the block design here. Okay, so that's number 10. Let's look at the next one. Number 11, you have developed a weight loss treatment that involves a combination of exercise and diet pills. The treatment has been effective with subjects who have used a regular dose of the pill of 200 milligrams when exercise level is held constant. There is some indication that higher doses of the pill will promote even better results, but you are worried about side effects if the dosage becomes too great. Assume you have 400 overweight volunteers for your study who have all been on the same exercise program, but who have not been taking any kind of diet pill. Design a study to evaluate the relative effects of a 200 milligram, 400 milligram, 600 milligram, and 800 milligram daily dosage of the pill. Okay, so it says here that we used a regular dose of the pill of 200 milligrams, and we know the effect has been effective. So when exercise level is held constant. Now, since exercise level is being held constant, that means we do not have to block for exercise level. okay? Because they're about the same exercise level among all 400 participants. It says 400 overweight participants who have all been on the same exercise program, right? So that means that we don't have to control for blocking, or we don't have to block for exercise control and exercise program to control for that. So we can simply break them up into the groups, randomly assign them into groups for 200, 400, 600, and 800. Now, because we know that the those that took 200, we know the results for that. That can serve as our control group. Okay, so this right here can serve as a control group because we already know the effects of getting the 200 milligrams, and therefore that can serve as our baseline so that if we increase the dose, we'll see if it's even further effective or not, right? That's what we want to see. So what we're going to do is randomly divide our 400 volunteers into the 4 groups, right? So we say we've got 400 volunteers. You got random assignment, right? You know, assign, you have 4 groups. Now you could include a placebo group, but it's really not necessary because you already have a control group, and you can just do it based off of the control group. You can compare them to the control group, okay? Because you already know the effects of 200 milligrams. So you can include placebo, but you do not have to. So in this case, we're going to have a control group, which is the 200 milligrams. You're going to have 400, 600, 800. And then you're going to compare their effects, right? Compare responses. All right, so there you go. So there's an example of that design there. Okay, so number 12, you are going to study the effectiveness of 3 different SAT preparation courses. You obtain 60 high school juniors as volunteers to participate in your study. You want to assign each of the 60 students at random to one of the 3 programs. Describe a procedure for assigning students to the programs. Now, part A, it says you want there to be an equal number of students taking each course. Okay, so there's different ways you can answer this question. You can use a random number generator. So you could say, okay, get the number, take each of the high school juniors, give them a unique number from 1 to 60, and then using a random number generator, generate, you could say you could generate 60 of those numbers, right, between 1 and 60 without repeat. And then you could say the first number corresponds to the student in group 1, the second number corresponds to the student in group 2, and the course 2, and then the third number corresponds to the student in course 3, and so on. And then just keep alternating like that. Or you can have the first 20 students in group 1, and the second 20 students in group 2, the last 20 students in group 3, whatever the case may be. So that you get an equal number of students, right? Now, another way to do it without a random number generator is you have 60 names on slips of papers and then randomly select the papers, right? Scramble them, the papers, of course, mix them well. And then the first student goes into program 2, then the next in the program 2, or whatever, and then keep doing like that until you get all 60 students assigned. The point is you want an equal number of students per group. Now, the next part is saying you want to assign them independently. So that means there doesn't have to be the same number of students per group. It just has to have the same probability of being in any of the 3 groups, right? So in order for us to do that, we could say if we use a random number generator, we can go from 1 to 3 since there's 3 groups, and then go to a student and then generate a number from between 1 and 3, and then that will tell us what group they go in, right? So first student, randomly generate. If I get the number 2, then they're going to go into group 2, and I do that for all 60 of the students until they get to their groups. Now, because it's independent, the chance of being in a particular group is 1/3. So it's the same probability for being in any of the three groups, right? Where that's not necessarily the case for Part A. There's the chances actually change as you pick more students and assign them into groups, right? So something to keep in mind. All right, so there is Part B. So let's look at number 13. In this, it says a researcher wants to obtain a sample of 100 teachers who teach in high schools at various economic levels. The researcher has access to a list of teachers in several schools for each of the levels. She has identified 4 such economic levels, A, B, C, and D, that comprise 10%, 15%, 45%, and 30% of the schools in which the teachers work. So this is 25. So this is a total of 100. Okay. Describe what is meant by a stratified random sample in the situation and discuss how she might obtain it. So remember, stratified random sample means you're splitting the population into groups, right? In this case, A, B, C, D. And then you're doing a simple random sample, or you're randomly selecting some people in each group, okay? And then that's how you do a stratified random sample. Now, ideally, you want to make it so it's representative of the population. So like if group A is only 10% of the population, then you might want to only grab 10% of your sample from that population, for instance. So let's go ahead and do that. So a stratified random sample would be a sample in which you get the proportion of teachers from each of the 4 levels is the same as that of the population from which it was drawn, right? So so basically, you're gonna make all the percentages the same that you're gonna draw from each group. So we got 100 teachers, right? So we got 100 teachers, a sample of 100 teachers, according to what they said. So how many of them will be in A? Well, I mean, it's 10% of that. So there's gonna be 10 that's in A. And then you got 15%, so 15 are going to be in B, 45 in C, and 30 in D, right? So you're going to break them up into the groups, and then you're going to randomly select 10 teachers from A, randomly select 15 teachers from B, 45 teachers from C, and then 30 teachers from D. Okay, and that would doing a simple random sample of all of those will give us 100 teachers, a stratified random sample. All right, number 14. You are testing for sweetness in 5 varieties of strawberry. You have 10 plots available for testing. The 10 plots are arranged in 2 side-by-side groups of 5. A river runs along the edge of one of the groups of 5 plots, something like the diagram shown below. The available plots are numbered 1 to 10. This is very similar to the question that we did in a homework, right? It's almost identical, like the type of thing setup where there's a stream and then there's 10 plots of land or something like that. So you decide to control for the possible confounding effect of the river by planting 1 of each type of strawberry in plots 1 to 5, and then 1 of each type in plots 6 to 10. That is basically your block to control for the river. So we're going to block by the columns rather than the rows, because if we block by the rows, they're not going to be the same. So if I block by 1 and 6, like that row, the first row, 6 is close to the river and 1 is not. So, 1 is close to the stream, the other one's not. So it doesn't make sense to block by that. So we're blocking by columns because these are close to the river, the 1 through 5 are not. Then within each block, you randomly assign 1 type of strawberry to each of the 5 plots within the block. What is the purpose of randomization in this situation? Okay, so the reason why, so let's say you're doing this block right here, you're going to randomly assign a strawberry into specific blocks randomly though, right? The reason why you do it randomly, right, is because you want to control for other variables. You want to control variables that might affect the outcome that you may not know about, right? So there may be, For example, differences in soil quality between 1 and 5. Who knows, right? Maybe 1 has richer soil than 5, and that will affect the growth or sweetness of the strawberry, right? Maybe the bacteria levels are different in soil 1 and 5 or something like that. And the bacteria might help contribute to compounds that might aid in growth and sweetness of the strawberry. Who knows? There's different variables that you just don't have control of. And so in order to help offset the effects of those variables, we can randomize where we put each type of strawberry and control for that. So that's the purpose of randomization. All right, so number 15, look at problem 14 again. It is the following year, and you now have only 2 types of strawberries to test. Faced with the same physical conditions you had in problem 14, given that you're concerned that different soil conditions as well as proximity to the river might affect sweetness, how might you block the experiment to produce the most reliable results? Okay, so this is interesting. So you only got 2 types of strawberries here. Before, if you looked at it, it says there were we have it says so you have a lot of different types of strawberries, but now you only got 2. And so they want us to control the effect of soil condition and as well as proximity to the river. Okay, so not only do we have to block by being close to the river, we have to block by effects that are effects of possible soil quality. So maybe 6 and 7 have different soil quality than 9 and 10, right? Because 6 and 7 are pretty close to each other, so they're kind of comparable, right? 9 and 10 are pretty close to each other, so they might be comparable. 8 is in the middle, so it's probably going to be different as well. But if you look at the north and south, 6 and 7 and 9 and 10, those are going to be for sure. There might be some significant differences there. So what we can do is do 4 blocks, right? So we got 1, 2, 3, 4. So block 1 is going to control for, they're going to be far from the river, but they're going to be the northern plots. Block 2 is going to be close to the river, but in the north plots. Block 3 is going to be far away from the river, but the south blocks. And then block 4 is going to be close to the river, but south plots. This allows for local variations in soil quality between north and south, as well as proximity to the river. So that way you can block for those 4 things. That's just an example of how you could do it. And then what you could do is then you can randomly assign 1 type of strawberry to each plot. So you have 2 types of strawberries, randomly assign, let's say you have strawberry A and strawberry B, you're going to randomly assign it to one of those 2. So let's say a random number generator gives me 2. Well, then that means strawberry A is going to go to 2, and then that means strawberry B is going to go to plot 1. So again, we have to still randomize within the block to control for the possibility that 1 and 2 might be a little bit different. Even though they're close to each other, they still might be a little different, or whatever the case. Maybe there's a little bit more sunlight in plot 1 than there is in plot 2. I don't know. So yeah, you have to control for that. All right, so there's number 14. Hopefully that makes sense, or number 15. Hopefully that makes sense. And we're almost done here. A couple more problems, 16 and 17. Number 16, a group of volunteers who had never been in any kind of therapy were randomly separated into 2 groups, one of which received an experimental treatment and therapy to improve self-concept. And the other group, the control group, received traditional therapy. The subjects were not informed of which therapy they were receiving. Psychologists who specialize in self-concept issues evaluated both groups after training for self-concept, and then the self-concept scores for the 2 groups were compared. Could this experiment have been double-blind? Explain. And if it wasn't double-blind, what might have been the impact on the results? Okay, so in this case, it's not double-blind, right? Because it says here, well, we know that if we look at this sentence here, the subjects were not informed of which therapy they were receiving. So it's single blind, but it doesn't say anything about the psychologists not knowing which group they were in, right? It doesn't say anything about that. So this will be a single blind experiment. A double-blind experiment is when you have the participants in the study as well as the researchers are completely do not know the participants in the study don't know which therapy they were receiving, and then the researchers or psychologists don't know which group the subjects were in, right? Which therapy they received. Okay, so it has to be blind for both of them. So it's not double blind. Now, if it was double blind, if it was not double blind, then that means that the psychologists know what therapy they're receiving, and so there's a good chance that the psychologist might have a little bit of bias, or they might interpret the results differently because they know that this group has the training for it or has this kind of therapy, and therefore they're gonna maybe inadvertently interpret the results in favor of one or the other, right? So it's important to keep that in mind. So that would have a drastic impact on the results or the interpretation thereof. All right, the last one, number 17, you want to determine how many students in your school feel about a new dress code for school dances. One group in the student council, call them Group A, wants to word the question as follows. As one way to help improve student behavior at school-sponsored events, do you feel that there should be a dress code for school dances? Another group, Group B, prefers, should the school administration be allowed to restrict student rights by imposing a dress code for school dances? Which group do you think favors a dress code and which opposes it? Explain. All right, so this is question wording bias, right? So question wording bias is we word it in such a way to influence the response. So we can see that the first group, Group A, favors the dress code. They mention as one way to help improve student behavior. That means that they feel that they should favor the dress code. And then the next one is, should the school admin be allowed to restrict student rights, imposing a dress code? So that negative tone, that negative language indicates that they're opposed to the dress code. All right, and guys, and that is it for the questions. There are a total of, I think, 20 questions in the exercises, so we've done basically most of them. I hope you found this lesson informative, and as usual, I'll see you in the next one.